Welcome to the fifth video in the series of short videos on stereoisomers. In this video, we will look at the various ways that rings can form stereoisomers. Starting with the beginning, the Fisher projections. As you recall, Emil Fisher said that basically you can determine which way a molecule will bend light by drawing a flat representation of that molecule. Fisher projection. In this, the carbonyl group found in a biomolecule, an aldehyde or ketone or a carboxylic acid, is on top. The terminal alcohol group is on the bottom. And the name is based on whatever substituent is attached to carbon 2. If that substituent happens to be to the right side of the carbonyl group, you now have the D isomer. If the OH or the NH2 is attached to the left side of the projection, you have the L isomer. Fisher attempted with this to describe the physical state or the physical organization of optically active biomolecules. However, something else happens with these molecules. Alpha and beta D-glucose are called epimers. They are carbohydrates differing in the location of one OH group. This can occur in many different ways. They are not enantiomers, but they could be diastereomers, meaning they're not mirror images, but they could be stereoisomers. On the other hand, they could also simply be structural isomers with no stereoisomeric interactions. The fact of the matter is, when you have epimers, they exist simultaneously. Essentially, as shown in the previous slide, they exist in equilibrium in water. In nature, the D version of glucose is the one that predominates. As the glucose is put into water, it is continually flipping between being a straight chain and either ring. This equilibrium is called mutarotation, and in nature, you get about 1/3 to 2/3 split between the alpha and the beta forms of D-glucose rings. Looking further into geometric cis-trans isomers, one finds a difference between straight chain versus ring organic molecules. For example, if you have a straight chain molecule, cis-trans isomers are limited to alkenes, where on opposite carbons on the double bond, the substituent can either be on the same side, cis, or across the double bond, trans. This is because the double bond can't rotate, so it creates a plane and keeps those substituents in place relative to each other. However, when one looks at a ring, things change. In rings, cis-trans isomers are going to be limited to alkanes. This can be shown as follows. If I have a cyclic alkene, it is planar. However, as you'll see, there's no relative difference between the side groups. If I look at 1,2-dichloropentene and look at the conformation in full, one notices that carbons 2, 3, and 4 have four substituents on them, allowing for either cis-trans relationships if they're differences. However, carbons 1 and 2 with the double bond each only have 3 substituents, which means the 2 chlorines are facing the same direction and can't oppose each other. There's no option as to which way they're going to face. On the other hand, you have those chlorines that, once again, are equatorial at all times. There's no option for another isomer. On the other hand, a cyclic alkene, since the ring is closed, it actually does create a plane because closing the ring prevents rotation. If you look at another molecule, 1,2-dichlorohexane, you'll see there's 2 ways to draw this molecule. One chlorine could be axial while the other one is equatorial, or both of them could be axial but on opposite sides. The first case creates, with both chlorines essentially on top, for want of a better word, a cis configuration. The second case, where one chlorine is pointing up and the other's down, is a trans configuration. You can see that these relationships hold no matter how the ring is actually flipped or rotated in its various conformations. When the cis bends, the chlorines both stay facing the same direction. And when the trans holds another conformation, the chlorines are still facing in opposite directions in the trans isomer. In greater detail, one finds something else. Again, here's the conformer of cis-1,2-dichlorohexane, where the chlorines relative to each other are both still facing in the same direction. The trans configuration, again, the chlorines are facing opposite directions. However, you have a chiral center created now, where you can have trans 1R, 2R, 1,2-dichlorohexane, where both of the chlorines are pointing outwards. Another option is to have trans 1S, 2S, 1,2-dichlorohexane, where once again it's trans because one chlorine's pointing up and one's pointing down, but on the carbon with different substituents, carbons 1 and 2, the arrangement of the chlorines has changed. So in this case, you have both types of geometric isomers coexisting, cis-trans and RS. When one has an alkane ring, cis-trans isomers, you have identical substituents on opposite ends of a carbon-carbon bond. Substituents on carbon A and the same substituents on carbon B. Those can be orientated 2 different ways. So, with the same molecule, 1,2-dichlorohexane, one sees with a projection figure both chlorines are pointing up in this case, which makes it cis. In the second case, the projection shows one chlorine coming out of the screen, the other one going backwards, which makes it the trans isomer. This holds true through all conformations. As one goes from a chair to a boat to the opposite chair, for the cis isomer, regardless of which conformation you have, the chlorine substituents in this case are going to be facing the same direction. That could either be both axial or both equatorial. Doing the same manipulations with the trans isomer, one gets the same effective result. One chlorine is going to be axial, the other one's going to be equatorial at all times, no matter what conformation the molecule's in. So the cis-trans relationship holds for the molecule in its entirety, no matter what conformation it's in. Additionally, the stereosenses are S-stereoisomers. If I look at the cis, chlorine 1 is S, counterclockwise, chlorine 2 is R. If I do the other cis isomer with both chlorines backwards, 1 now becomes R and 2 becomes S. These are non-superimposable images, but they are stereoisomers, so I have Diastereomers. On the other hand, I still have 2 stereosenses on the trans as well. As drawn, S and S. If I flip to the other trans configuration, I now have R and R. In this case, in the trans situation, you do have mirror images, so you have enantiomers. In general, chirality in alkane rings seems confusing, but there's one simple way of looking at it. In order to have a chiral center, one still needs an sp3 carbon with 4 different groups attached. So here I have 2 separate molecules. The easiest way to find the chiral center is very simply to name the compound. In the first case, I have ethyl 4-methylcyclohexane, and in the second case, I have ethyl 3-methylcyclohexane. Those carbons that are numbered are going to be possible chiral centers because they're different. Carbons 1 and 4 or 1 and 3. They're both all 4 of these carbons have sp3 hybridization. There's no double or triple bonds, so they're still possibly chiral. Do they have 4 different groups? At this point, you know there's an H on each one. There's 4 substituents. The question is, the other 2 substituents are going to be part of the ring. How do you tell it's chiral is actually rather simple. As one goes around the ring, clockwise or counterclockwise, one essentially just looks around. If you get the same view, if there's a mirror plane, that means the molecule is not chiral. No matter which way you go across 1,4, you get the same view. If the mirror plane, or the plane between the opposing points of the chiral carbon, shows a difference, that means you do have a chiral center. In the second case, going clockwise from carbon 3 leads you to the methyl group on 2 carbons away. 2 carbons away going counterclockwise just leaves you with a CH2 group. It's a different point of view, so you have a chiral center. I hope you found this video useful and interesting, and thank you very much for listening.